Hello, my dear student. I'm Saktwala from Educatiz. Welcome again for our discussion for our subtopic topic of rotation of rigid body. For our subtopic on access theorems rotating boats. So, my dear student, as we tried to see on the last session, we said that the perpendicular axis theorem give us the relationship between the moment of inertia along to the x-axis and also the moment of inertia along to the x-axis plus the moment of inertia along to the y-axis. That is what we tried to see on the last session. And after there, we looked about how can some examples related with the perpendicular axis theorems. So after this one, my dear students, we tried to see the application of the perpendicular axis theorem. How can it be applied? And now we are going to proceed with one of the application of the perpendicular axis theorem, which say that moment of inertia of a lamina rotating about an axis perpendicular to the plane. Now imagine we have this lamina, and this lamina try to rotate perpendicular on an axis to the plane. Now how can we obtain the moment of inertia? That is what we are going to observe for our discussion here. So consider a mass of m with a dimension x, y, rotating about about an axis or y, passing through its center or perpendicular to the plane on figure number 15 for the topic number 4. So the moment of inertia of this axis can be determined using the perpendicular axis theorem. So imagine we have this lamina, and the lamina contain the mass m, which trying to rotate on an axis, and this lamina having a dimension which is x, y planes. Try to rotate on an axis along to the y axis, or y, as we try to observe here. So this OY passing through the center, and when it is passing through the center, the lamina try to undergo perpendicular along to that an axis, as it is shown on our figure number 15. So how can we obtain the moment of inertia? It's what we are going to try to observe. So our figure, as we observe here, our figure number 15 for our first topic, give us the explanation how the lamina try to rotate on an axis at its center, as we try to see the nature of the lamina. That it is looked like the uniform load, as we try to demonstrate. It's like the rectangle, as we try to observe. Now we have the axis of rotation, which is xy. Tuna axis yetu ya rotation ambao ni xy, and also this xy passing through the center O, as we try to see. But the distance from this center here, this center O, up to the this point should be equals to b, as we try to demonstrate here. And also the distance from this axis of rotation, which is xy, must be equals to a, as we try to see that the distance from the axis of rotation until to the this line here, vertical line, must be represented by a. And also the distance of this lamina, it means the length of the lamina from this point up to that point must be represented by the axis, as we try to observe. And also, my dear student, we have the distance from this point up to this point. It means that the width of the lamina plane, which is equal to y. And after this one, this on the element here on the plane, we have the elemental line, as we try to see, we have the element of the small change of B, because if the distance here from this center up to this point must be equal to B. Now, the small increase of the B here must be equals to the B. It can be represented by the B. But also for the vertical one, the small increase must be represented by the A, because the distance from this one we have is A, and also the small increase must be represented by the dA, as we try to observe. So, my dear student, how can we demonstrate, how can we get the moment of inertia for the lamina using the perpendicular axis theorem? As we see that this lamina trying to rotate perpendicular to the axis of rotation along to the xy, it undergo perpendicular, as we observe here, the direction of the angular velocity, that the lamina moving try to rotate perpendicular on it is an axis, but it passing through the center. It means this point, the horizontal line here, the axis is also the x, and also the vertical axis is on y, as we try to see, my lovely students. So after this one, now this lens here, it means the parallel one, as we try to see the axis of rotation from this line up to this should be represented by L, as we try to observe. So how can we get the moment of inertia for the lamina? That is what we are going to try to demonstrate on our discussion here. So consider a mass M, consider a small mass element dm rotating at a distance from the axis OI. Now imagine we have the small mass element dm, and this small element mass dm rotating at a distance from the axis OI. So the moment of inertia di along to the y of the dm about the axis can be expressed by this one. So for along to the y-axis, we should obtain the moment of inertia by taking di, because we are talking for the elemental. It means for the small change of the mass. We can say that along to the y-axis, the moment of inertia, the small change of the moment of inertia must be equals to a square times dm. Kwa tutaangalia hapa along to the y-axis hapa kwamba along to the y-axis we should obtain the moment of inertia. It means di along to the y-axis must be equals to a square, then we times by the dm, as we try to observe. This will be our equation number 53 for our fourth topic, my dear students. So after this one, let us go and focus for another axis, as we see here. So since dm is a fraction of the total mass, the way we know that dm represents the fraction of the total mass m of the lamina. Now the mass and the area both of the lamina and the small element can be represented at this one. So until we started this topic here, we tried to see that dm always represented the fraction of the mass m of the lamina. If it represents the total mass m of the lamina, now the mass m, the mass and the area of the both lamina and the small element, we are going to look for the variation, the relationship between the mass of the lamina and also the mass of the element, or the area of the element of the lamina. This element, as we try to observe, this is an element, and also this is an element. Now we are going to see the whole mass, the relationship between the whole mass of the lamina and also the mass of the element compared with the area. Now we say that dm divided by dA must be equal to m divided by a, but dm here represented the mass, this dm represented the small change of mass. this represent the small change of mass for the element. It means for the element, the small change of mass for the element on the lamina that are found inside the lamina. And also the here represent the small change, the small area. It means here hapa ina represent area, small area, while this M, the largest, the capital M here represent the mass of the lamina, and the A represent the area of the lamina. So now we could say that this should be our equation number 54. This must be our equation number 54 for our 4C topic, my dear student, using the comparison between the dm that give us the fraction of the total mass m, and also the mass compared with the area, as we try to see kwamba kumbe fraction of the mass of the small element must be equal to the fraction of the mass of the element, where m represent the mass and also a represent the area of the lamina. So after this one, my dear student, in equation number 4.54, now as we recall our equation number number 54 here on our fourth topic, we say that the area of the lamina is xy. Kwa ile area ya lamina tunaipata consider ile xy should be obtained using the x in the xy, and also the area dA of dm is yda. Kwa huyu area wa ile lamina along to the xy atabini obtained the area A of the lamina is xy. Kwa yule area kwenye lamina atakuwa ni sawa na xy, while the area of the area dA of the dm is equal to yda. This should be the way we can obtain the area, and also the area for the lamina, and also the area for them. The area for the dm, and we say that the area for the lamina we must take their area must be equals to x times a, while the x times y this means that the length times width, lakini kwenye length pale tulikuwa na x, lakini kwenye y tulikuwa ni sawasawa tulikuwa ni sawasawa kwenye width tulikuwa ni sawasawa na y, therefore area yake itakuwa ni sawasawa na xy. And also the area dA of dm is yda. Kwa area sasa tuweze kupata area wa dm should be obtained equals to yda. Kwa dA mkubwa atakuwa ni sawasawa na y times the dA. How can we get this dA? This dA we tried to see that the distance around to the y. It means kwamba kale ka distance ka kutoka kwenye axis of rotation ya ile OY paka kwenye point, paka kwenye ile small element along to the x axis, kwa toka tatupatia sana sana the dA. So after this one, my lovely student here, what we can do here after looking, after obtaining dA is equal to yda, what we should do here. Now let us consider x the moment of inertia along to the y axis. And our moment of inertia along to the y-axis must be equals to 2 times m over x integral from 0 to x divided by 2, then we times it by a square dA. But we know that here, my dear students, we know that this x here, we have tried to observe this x must be equals from our figure x must be equals here x should remain the constant. Now we are going to integrate. Now we should factor out a square here. Kwamba here let us factor out a square, and after factoring out a square we should remain inside ni 1 over itakuwa ni 1 over x. But we are before we factor out, let us consider that at the moment of inertia along to the y-axis must be equal to 2m divided by x. Then we integrate from 0 to x divided by 2 times a square dA. Because we are integrating with respect to a, if we integrate with respect to a, we should integrate here by adding 1 for exponent and divide by the exponent after adding 1. It means integration of x power n is dx is equal to x power n plus a, then we divide by n plus 1. That is the principle we use so as to integrate. So here, if we integrate from the limit 0 up to the x divided by 2, we should obtain must be equal to 2 ma cube. This must be ma cube after integrating, because if we integrate, we add by 1, and also we add by 1 and also divide by the exponent. It means 3. Tamaanisha itakuwa ni 2 ma power 3, then we divide by mx power divided by 2x, and we introduce the limit. If we introduce the limit here, because this a change, if the a change, my dear student, we could say that the remaining one is that the remaining must be equal to m over 12, because if we substitute here x over 3, itakuwa ni x power 3 divided by 8. It means divided by 8 times 3, then at the top we have the 2. If we simplify, tutapata ni sawa na m over 12 times the x square.